Here's some more examples just to continue section 1.8. Kind of like what we did in a previous section where I had you guys sketch a possible graph. Again, this is what could happen here, but there's going to be some things that have to appear in the graph. So we want to sketch a possible graph that is discontinuous at x equals -1, 2, and 4. It will be continuous from the left at x equals -1 and from the right at x equals 4. So go ahead and pause the video, see what you can come up with, and then just double check by continuing to play. All right, I'm going to actually start with continuous from the left at x equals -1. I could put a point anywhere, open or closed. Let's say I want to put it right up here, and I'll make it closed. So we know we're going to be continuous from the left, so I have something like this. And it doesn't matter if I put an arrow or an endpoint right here. That part doesn't matter. We just know that we are continuous from the left as x is approaching -1 from the left. The limit here is going to actually equal f of -1. But now it's discontinuous at x equals -1, so we're looking kind of at both sides. So that all that means is I just need to put another point. In this case, it would be an open point, perhaps right here. All right, we also know continuous from the right at x equals 4. So again, I could put a point anywhere here at 4. Continuous from the right, so then maybe I have something that looks like this. So that the limit as x is approaching 4 from the right is equal to f of 4. But we also know that we're discontinuous at x equals 4. So again, I could maybe put a point that's right up here. All right, so we already took care of the x equals -1, x equals 4. We also have a discontinuity at x equals 2. So all that really means is I could put an open endpoint. It could be a jump discontinuity. So again, I can maybe just put a point right here and then just connect with any type of line or curve, something that looks like this. I don't want to make that look like it's a closed endpoint. So we could have something that looks like this. And that's one possibility. What matters is that all of this information is met, all the requirements are met. All right, so in this example, it says suppose f and g are continuous, and we're going to see that a lot in the statements here. Suppose that they're continuous functions such that g of 3 is equal to 4, and the limit as x approaches 3 of f of x plus 2 times g of x is equal to 15. We want to find f of 3. All right, so we're going to start with g. So if g is continuous, what that means is the limit as x approaches 3 of g of x, we're going back to that definition from the first part. So the limit of g of x as x approaches 3 is equal to g of 3. And we have this right up here that this is equal to 4. So then the limit of g of x as x approaches 3 is equal to 4. We also know that if f is continuous, and then they're telling us that it is, or I should say since f is continuous, then we would also know that the limit as x approaches 3 of f of x is equal to f of 3. So that's what we're going to do. If we could find this part right here, then we will know this part right here. And that's where this part is going to come into play. So I know if I have the limit as x approaches 3 of f of x plus 2 times g of x, that's equal to 15. We could use our limit laws to separate this. So now this becomes the limit of f of x as x approaches 3 plus, I could say, 2 times the limit as x approaches 3 of g of x is equal to 15. You guys pause the video, see if you could figure the rest of this problem out, and then go ahead and continue. But what we would do next, still keep the limit as x approaches 3 of f of x plus 2, and then this is where we're going to use the 4 right here. So 2 times 4 is going to equal 15. So we get the limit of f of x as x approaches 3 plus 8 equals 15. And then the limit of f of x as x approaches 3, just subtract 8 from both sides, is going to be 7. So since f is a continuous function, then the limit of f of x as x approaches 3 is also equal to f of 3. Therefore, f of 3 is equal to 7. But that's using the definition of continuity, that f of 3 needs to exist, which it does because they're telling us that f is continuous. So we know f of 3 exists. The limit of f of x as x approaches 3 exists, and they're equal to each other. So this statement right here allowed us to say that f of 3 was equal to the limit as x approaches 3, which is equal to 7. All right, so again, we're going to go back to using the definition of continuity. We want to show that f of x is continuous at x equals 2 using this definition. So step 1 of the definition, we need to ask ourselves, does f of 2 exist? So all we have to do is figure out f of 2. And technically here we do have a polynomial function. If we were to expand this, it would be a polynomial, so we could kind of understand that polynomials are continuous everywhere, but we're using the definition, the pieces here to show that. So f of 2 is going to be 2 times 2 plus 2 cubed squared. So this will give us 4 plus 8 squared. 12 squared is giving us 144. So we can answer yes, f of 2 is equal to 144. Second question is, does the limit of f of x as x approaches 2 exist? So we would take the limit here of 2x plus x cubed squared, that quantity squared, as x approaches 2. Now again, we have no issues here. We could just do direct substitution, which we could tell is going to be the same as a substitution that we did above. So this could just become 2 times 2 plus 2 cubed squared. No need to show from the left or from the right. We only do that if direct substitution is not possible. So again, this is going to give us 4 plus 8 squared, which will give us 144. So yes. Limit of f of x as x approaches 2 is equal to 144. And then our third question is, are they equal to each other? So does the limit of f of x as x approaches 2 equal f of 2? And the answer is yes. We just showed it in steps 1 and 2. We get 144 for both of them. So now we could say, therefore, f of x is continuous at x equals 2. All right, in this example, this is that removable discontinuity that I was showing you in part 1 of this section. Here we have a piecewise function, and what we're looking at here is this first piece is actually it's going to exist as long as x doesn't equal 2, but notice if x equals 2, we're going to have a problem in our denominator. We're going to get a 0 there. So if you were to cover up, let's see, the second piece, if we were to just look at g of x here, we would say g of x is not continuous at x equals 2. So what we want to do is just fill in that missing piece. So I just want to show you first what g of x simplifies to for the first part here. So if I were to take the x cubed minus 8 over x squared minus 4, right now we don't know what the graph of this looks like, but maybe it simplifies into a line or a parabola, something that would just have an open endpoint or a hole somewhere. So that numerator is actually a difference of cubes. So if you remember, we want to factor into binomial and a trinomial. Cubed root of x is x, cubed root of 8 is 2. I'm going to use the same sign. In the trinomial here, remember I do x times x, which is x squared. In the middle, I do 2 times x. And at the end, I do 2 times 2, which is 4. So if I have the same sign, then I'm going to have the opposite sign, and the last one is always positive. Over x minus 2, x plus 2. And then this will just simplify. The x minus 2's will divide out. So because we do have this extra x plus 2 down here, it's still a rational function. So we just end up with x squared plus 2x plus 4 over x plus 2. So it's not just a simple line or parabola, but we're still going to get a hole. No matter what this graph is, we would still get a hole at x equals 2. So what we have to do is figure out a value of p when x is equal to 2. So imagine whatever this would graph, we would just have a hole. So I'm just going to draw like a piece of it. So if we have something that maybe looks like this, and right here at 2 we have a hole, we need to just fill that in. So that's what we're going to do. All right, so in order to make g of x continuous, I need to know part of the definition, that third step. So I know that g of 2 is going to exist because that's what I need to find. So in other words, we want to find g of 2, and I know that that's going to equal the limit of g of x as x approaches 2 here. And I know the 2's because this is what number is right here. If that were a 4, I would be using as x approaches 4. So the limit of g of x is going to equal g of 2. Well, now that we simplify g of x, this is what we're going to use for our limit. So I'm going to say the limit of x squared plus 2x plus 4 over x plus 2 as x approaches 2 is going to equal g of 2. So I could just do direct substitution here. So I'm going to get 2 squared plus 2 times 2 plus 4 over 2 plus 2 is going to equal g of 2. So this is going to give me 4 plus 4 plus 4, which is 12 over 4 is g of 2, which is 3. All right, so there's a couple ways we could do this. This is just one of them. So now I could say to make g of x continuous, here is my piecewise function. Again, I could start with what I had originally. We have the x cubed minus 8 over x squared minus 4, as long as x does not equal 2. But then right here, that p, so we could say, let's let p equal 3. So now I could put that 3 in here if x is going to equal 2. And what that would do, if you look right back up here, is no matter what our graph looks like, that's going to fill in that hole and then make that continuous. Or, to me, this is the simplest way to do this. Or you could say we have g of x is equal to the x cubed minus 8 over x squared minus 4, as long as x doesn't equal to 2. And then we could take what we got simplified here. So it's this part right here, because what that's going to do is just graph this part right here without the hole. So we could just say it's equal to x squared plus 2x plus 4 over x plus 2, as long as when x is equal to 2. And again, that fills in the hole. But what we wanted to do here was define p. So p could be this function. So we could let p just be this new function once we factored out the x minus 2's and divided those out. So those are two ways to do this. Again, finding a specific value that fills in that hole, it removes that discontinuity. All right, in this example, we want to find the x value at which f is discontinuous and determine if f is continuous from the right, the left, or neither. So here is our piecewise function that we're going to be looking at. Now remember, going back to the definition, our special numbers here are 1 and 4. So first we need to determine, does f of 1 exist? And because these are all polynomial expressions here, yes, they're going to, but we need to find them. So f of 1 tells me I'm going to use this top one here. So this is going to become 3 minus 1 squared, which is just going to give us 2. So f of 1 exists, and it is equal to 2. Our next special number here is 4. So f of 4, I'm going to use the middle one because that's where x is also equal to 4. So we're just going to get 4 plus 1, which is equal to 5. So we know what the f of c, in this case 1 and 4, are going to be. Next, we need to find the limits. So we're going to take a look at the limits from the left and from the right here for 1. So first I want to show that the limit of f of x as x approaches 1, we'll do 1 from the left first, because we need to determine if the limit actually exists. So we need to find the two one-sided limits. And if it exists, is it going to equal 2? So the limit of f of x as x approaches 1 from the left. And again, we're using the first one here because that's where x is less than or equal to 1. So I'm just going to show that this is 3 minus that 1 squared, which is 2. So I'm also just going to add here. So this is also equal to f of 1. So we do have continuous from the left. Let's check continuous from the right. So if I'm looking at one from the right, I'm using the middle one that's right here. So this becomes 1 plus 1, which is also equal to 2. So because these two are the same, we could say the limit of f of x as x approaches 1 is equal to 2, which is equal to f of 1. Therefore, f of x is continuous at 1. Okay, so far no discontinuity. And let's check out the limits as x approaches 4. So now if we have the limit of f of x as x approaches 4 from the left, we're going to use the middle one that's right here. So this is going to equal just 4 plus 1, which is equal to 5, which also equals f of 4. So we know f of x is continuous from the left. Let's check out from the right. But notice these are all the necessary steps we need to show. All right, so from the right, I'm using the bottom one. So I'm going to get 4 minus 3 squared, which is going to give me 1. So here we would show, so this is not equal to f of 4. So we could say, therefore, f of x is not continuous at 4, or is discontinuous at x equals 4, but it is continuous from the left. But f of x is continuous from the left at x equals 4. All right, but again, we have to go through the definition. First, we want to define f of 1 and f of 4. So this would be step 1, finding these two right here. Next, we took a look at the limit of f of x from either side for as x approaches 1 from the left and from the right. We also compared it to f of 1. So even down here, that was equal to f of 1. So the limit exists here because they both, the left-hand limit and the right-hand limit were both the same at x, or at 2, or equals 2. And then they were also equaling f of 1. So that's meeting all three conditions of the definition. Therefore, this allowed us to conclude this part here. So this would be step 2. And then step 3 was determining if the limit existed at x equals 4. So we looked at each one-sided limit and then compared it to f of 4. So this would be step 3. All right, here we're going to take a look at another piecewise function. Let me write this up here. All right, so carefully copy this down. I know they're using a lowercase r and a capital R, so just be very careful here. But we're asking, is f continuous at r equals r? Lowercase r says it's just like asking at x equals r, but in this case we're using a lowercase r when it's equal to capital R. So again, we want to go back through the definition. So step 1 is to ask ourselves, does f of r exist? So what we would do here is f of r. So when I'm able to say that our x value is equal to r, we're looking at this part right here because that's when r, lowercase r, is equal to capital R. That's right here. So I need to use the bottom part. So this means f of r is going to become, using this expression right here. Actually, I want to use a capital R. That's in here. So sorry about that. We want to use a capital R because I got to replace the lowercase r with it. So GM over, and this just becomes capital R squared. So that's what we're looking at here. So we could actually substitute this in and just say that f of capital R is equal to GM over R squared. Step 2 is to ask ourselves, does the limit of f of r as lowercase r is approaching capital R, will that exist? So in order to do that, we need to separate this. So we have the limit of f of r as lowercase r is approaching capital R from the left, and then we have to figure this out from the right as well. All right, so if r lowercase r is approaching capital R from the left, that means lowercase r is less than r. So I'm going back up to this part right here. So this will become gm times capital R. I could just do direct substitution over r cubed. And then simplifying this, I get gm over r squared. And then the limit of f of lowercase r as lowercase r is approaching capital R from the right, that means r is going to be, lowercase r is going to be greater than capital R, so I'm looking at the bottom one. So this will become gm over capital R squared. So now these two are equal, therefore we can say the limit of f of r as lowercase r approaches capital R is equal to gm over r squared. Now we're looking at step 3 that should say that this limit needs to equal f of r. So this is equal to this right here. So yes, we would say, therefore yes, f of r is continuous at lowercase r is equal to capital R. This is just taking, instead of picking a specific value for an x value, it's really turning more towards the abstract. Again, I know it's confusing with the lowercase r and capital R, but you will see an example like this in WebAssign. So if it helps, you can turn these into maybe an x and a number, or maybe just an x and then the capital R, so you're not getting confused with the lowercase r. All right, now we just have one more example. Here we want to find the values of a and b that make the function f continuous everywhere. So again, it's just going back on the definition of continuity, but pause the video and copy this down. So again, we have two special numbers over here to the right. We have 3 and 4. So step 1 is that we want to determine, does f of 3 exist? Does f of 4 exist? Because if neither one of those exists, then we would right there say that our function is not continuous at those values. All right, so f of 3 means I'm going to use the middle expression here because that's where x could be equal to 3. So I'm going to say we're going to have, and careful here because we still have an a and a b. So a times 3 squared is going to give me a 9a minus b times 3, so minus a 3b plus 4. So that's what f of 3 is equal to. And f of 4, I'm going to use the bottom one here because that's where x is equal to 4. So I'm going to have 4 minus a plus b. So those are the expressions to help us figure out f of 3 and f of 4. All right, step 2 is about the limits. So I want to take a look at each one-sided limit here. So for limit of f of x, we'll start with x approaches 3 from the left. So 3 from the left means I'm using this top one that's up here. So this becomes the limit as x approaches 3 from the left of x squared minus 9 over x minus 3. I need to factor this. So this will just become x minus 3 over x plus 3, or times x plus 3 over x minus 3. So this will just give me x plus 3 here, which will give me a 6. All right. So again, we're asked to find the values to make f of x continuous. So I found an expression for f of 3, and it should exist. I just, again, where the a and b values are missing. So what this is telling me, so I have f of 3, I have an expression. I found the limit of f of x as x approaches 3 from the left I want to find it from the right. All right, so if I'm approaching 3 from the right, I'm using the middle expression here. So again, I'm going to substitute a 3 in for each one, which is actually just going to turn back into f of 3. So we're going to have, this will just become a 9a minus 3b plus 4. So I need the limit to exist, so that means my left-hand limit needs to equal my right-hand limit. So these two need to be equal. So I'm going to say 6 is equal to 9a minus 3b plus 4. So again, this is working because this is my left-hand limit, this is my right-hand limit, which also is equal to f of 3. So I'm just setting this up here for right now. I'm going to go through the same process for f of 4. So here I have the limit of f of x as x approaches 4 from the left. So if I go back up here, 4 from the left is this middle expression. So now x is 4, so I'm going to get a 16a. And then we're going to get a minus 4b. And then plus 4. And then the limit as x approaches 4 from the right, I'm using this bottom one here, which again matches f of 4. So this is going to just give me 4 minus a plus b. So now I'm going to set these two equal to each other. Now I need to find a and b. So what we did here was we were able to plug in all the x values. This is going to set up two equations, and we have to go back to algebra to remember how to solve a system of equations. So here I just want to get a and b on the same side and all my constants on the other. So I'm going to go ahead and add a. So this will give me a 17a, subtract b, so minus 5b, and then this is going to give me a 0 when I subtract 4 from both sides. Down here, let's just subtract 4, so I'm going to get a 2 is equal to 9a minus 3b. So I'm going to set both of these equations up as a system to help me solve for a and b. So I have 17a minus 5b equals 0, and I'm just going to switch this around. 9a minus 3b equals 2. So I'm going to use the elimination method here. I'm going to multiply this top equation. Let's say we multiply it by 3. I want to get rid of the b's. The bottom equation I want to multiply by a negative 5. So now this will give me a 51a minus 15b equals 0. Then we'll get a negative 45a plus 15b equals negative 10. I just multiplied everything in here by negative 5. In the top one, I multiplied everything by 3. So the 15b's cancel out. I'm going to get a 6a equals negative 10. Divide by 6 and simplify. So we're getting a negative 5/3 for a. And all I have to do is substitution step here. I'm just going to go back to this one. So if I have 9a minus 3b equals 2, I'm getting 9 times a negative 5/3 minus 3b. Don't need the parentheses there. Is equal to 2. So 3 goes into 9 3 times, so I'm going to get a negative 15 minus 3b equals 2. Add 15, so negative 3b equals 17. b equals negative 17/3. So here's my value for b, here's my value for a, problem solved. But going through the process again, not that this first part was really necessary, but it's still good to show that we have f of 3 and f of 4, the expressions there, because in this step right here, this was equal to f of 3. So we have the limit equaling f of that c value. Same thing over here. We have the limit that's existing if we can find the values of a and b, and then this was also equal to f of 4. So very important to keep going over that definition. Know those 3 requirements of the definition of continuity. All right, so this wraps up section 1.8. As always, guys, please let me know if you have any questions.